In the previous lecture, we have seen the different types of slopes, whether there is an infinite slopes, finite slopes, and their analysis. Now, today's lecture, we will just come to the part that is the infinite slope. So, infinite slopes are basically the slopes which are a natural slopes, such as the slopes which are used for the hills and mountains, which is having a length very long. In that case, again, we will categorize the analysis for the different types of soil, for the cohesion-less soil, for cohesive soil, and for the C5 soil. Right? So, first we will see the analysis for the cohesion-less soil. Analysis for cohesion-less soil. When the soil is a cohesion-less soil, which types of soils are these? These soils are the sandy soils. These soils are sandy soils. Now, sandy soils, if the soil is of a completely sandy nature, in that case, the value of C is equal to 0. Value of C is equal to 0, and therefore, the shear strength parameters are shear strength parameter shear strength parameter is phi only. Means whatever is the strength to the soil, that is only due to the angle of shearing resistance, that is phi, where the cohesion component is 0. Now here we will consider a slope which is, here we can just consider this is the slope. This slope is making an angle beta with the horizontal, making an angle beta with the horizontal. So here we will just consider a small wedge of the soil. Here we will consider a small, suppose this is the small wedge that we will consider, and the dimensions are A, B, C, and D. So this is the small wedge that we have taken into consider, where there are two major components which are acting on a wedge, that is the tangential component, that is the shear strength component, which is acting in the direction of gravity, and another is the resisting force that is acting as a normal force which is acting in the upward direction. And the another important is the self-weight of the wedge. So here, this self-weight of the wedge, before that considering this, we will just consider this D is the width and Z is the height of this wedge. Z is the height of this wedge and D is the width of this wedge. D is the width. Then there are the components which is called as the self-weight component. Here we can consider this W is the self-weight of the soil wedge ABCD, which is acting in the vertically downward direction. Now suppose I will consider this is the component, vertical component of the W, which is acting vertically downward. Which is acting vertically downward, and in that case, there is a normal component. This is the normal component, and this normal component we will consider with the N, or many times we will consider it as sigma. This is the normal component which is acting vertically, which making an angle with the vertical, and that is the component of a W. Then the another component, that is the tangential component, which is considered as T. That is the tangential component which is considered as T. Here, this consider a small wedge. Now we will consider a small wedge. ABCD of length D and depth Z. Length D and depth Z. Then following are the forces acting on it. Forces acting on it, on the wedge. So first is the weight of the component. First is weight of the component of the weight. So how we will determine the weight of these weights? The weight of these weights is the cell area or the volume multiplied by the density of the soil. Now here we will consider it was the infinite slope, therefore we will consider the length component is a unity. And therefore, what is the area? Area is B into Z. So here that will be W is equal to B into Z into L is considered as 1 into density. This density is the unit weight of soil. This is unit weight of soil and this is denoted by tau. Now here, then the N is the normal component and tau is the tangential component. Then the component of W parallel to the slope. Component of W parallel to slope. Component of W parallel to slope. Which component is parallel to the slope? Which component of W is parallel to slope? That is the T is the tangential component which is parallel to the slope and that we will denote by the T. So what is T then? T is W sin beta. In that case, this T is W sin of beta. T is W sin of beta. Then the next component is the component which is perpendicular to the weight. The perpendicular to the slope, that is component of weight perpendicular to slope and that is denoted by L. That is denoted by L and which is represented by L is equal to W into cos of beta. W into cos of beta. So there are three components. First is the weight component of the weight, which is actually the weight, that is the cell area of this weight multiplied by density. Then there are two components of the weight. One is parallel to the slope and another is perpendicular to the slope. Perpendicular to the slope is normal component, which is shown with the W cos beta and the another is W sin beta. Then W sin beta. Then here the force that cause the slope slide. Here, which is considered to be the activating force and another is a resisting force. Now here you can see the force which is acting in the parallel direction, parallel to the slope, then it will be called as resisting force, whereas the perpendicular is considered as a resisting force and parallel is considered as a sliding force, which cause the sliding of the wedge, which allows or which we just try to move the wedge vertically downward towards the gravity. So this force which cause the movement of the soil mass is called as a activating force, and then the another force, that is the normal force which try to resist it, is called as the resisting force. So here we will consider T is a sliding force, T is a sliding force and N is the resisting force. So here T is sliding force and N is a resisting force. One which cause the sliding miss, which will be responsible for the failure of the soil wedge or the sliding of the soil wedge, that is called as sliding force. So here this tangential force is considered as a sliding force and normal force is considered as a resisting force. So what is T? T is W sin beta. What is N? N is W cos beta. Now here this T is W sin beta and here this L is W cos beta. W cos beta. Now tell me, what is the equation of shear strength? Equation of shear strength tau is equal to C plus sigma tan phi. Tau is equal to C plus sigma tan phi. Now here, as the soil is a pure cohesionless soil, therefore the C value is 0. C is 0 as soil is a cohesionless. Soil is cohesionless. As soil is cohesionless soil, therefore this tau is equal to sigma tan phi only. Tau is equal to sigma tan phi only, means the shear strength in the soil is due to angle of shearing resistance only because the cohesion component is 0. Now here, what is this sigma? Sigma is basically the normal force. Sigma is basically the normal component. Therefore, this sigma will be replaced by n. Sigma is replaced by n, and therefore tau is equal to n into tan phi. Now what is n? N is W into cos beta. So here this tau is equal to W into cos of beta into tan. Cos of beta into tan of phi. So in this case, it will be W cos beta into tan phi. That is actually the normal component. Then the tangential component we already know. Then what is meant by factor of safety? Here the factor of safety is resisting force upon sliding force. Now what is resisting force? Resisting force is a normal force and sliding force is the tangential force. So in this case, what is resisting force? Resisting force is W cos beta. Resisting force is W cos beta into tan phi divided by W sin beta. Because this N is the resisting and this is the strength. What is resisting? Strength is the resisting force. Therefore, the normal component is the resisting force and sliding component or the tangential component is the sliding force. Therefore, what is factor of safety? Resisting force upon sliding force. So, what is resisting force? Resisting force is a shear strength. Divided by sliding force. So here we will just take this value of shear strength from here and it will be W cos of beta into tan of phi divided by W sin beta. It will be W into sin of beta. Now here, as this W is getting cancelled, this W is getting cancelled, sin will take this cos beta into the denominator. Therefore, this sin by cos is tan beta, and therefore here the factor of safety is equal to tan phi upon tan of beta. Tan phi upon tan of beta. So if this tan phi upon tan beta. Now here, this tan phi factor of safety in cohesionless soil, it will be tan phi upon tan beta. What is phi? Phi is the angle of shearing resistance and beta is the angle of slope. And always remember that when this beta is less than phi, always your slope is in a stable condition because this angle of repose is having more value than the actual slope. In that case, it will be a stable slope. When this phi is less than beta, in that case it is called as unstable slope. Unstable slope. So here this factor of safety is tan phi upon tan beta. It is the case for the cohesionless soil. Now here, if suppose your factor of safety is what? If suppose your in case of the limiting equilibrium, in case of limiting equilibrium, in case of limiting equilibrium, what is the case of limiting equilibrium? In limiting equilibrium, the value of factor of safety is 1. So this is the case of limiting equilibrium. In this case, when your factor of safety is 1, in that case, your angle of tan phi is equal to tan of beta. Tan phi is equal to tan of beta, and when this tan we will just cancel it. In that case, it will be phi is equal to beta. Phi is equal to beta, where the factor of safety is 1. When we plot the graph between shear stress versus normal stress. So here I will consider shear stress, and over here it will be a normal stress. This is the two components which we have taken into consideration. Here, what is this? This is phi. This is phi, and here this is Morse Coulomb strength envelope. That is the Morse Coulomb's strength envelope. That is the limiting equilibrium. Here, this phi is the envelope internal friction where the soil is a purely cohesive soil. The shear strength component C is 0, and therefore the strength envelope is passing through the origin, which making an angle phi with the horizontal. Right? In this case, when your angle is less than, this is suppose the slope angle. This is suppose the slope angle. This slope angle making an angle beta. Making an angle beta. In that case, this is a flat slope, which is considered as a stable slope. Which is considered as a stable slope. Whereas, when this beta is more than phi, in that case, it will be called as unstable slope. This is suppose angle beta, then it will be called as unstable slope. In unstable slope, beta is greater than phi. And here, this beta is less than phi. In that case, it will be in a stable condition. So here, this is the case of limiting equilibrium where phi and beta are same. This is the case of flat slope where the slope is a stable slope where beta is less than phi. This is the unstable slope where beta is greater than phi. There, the factor of safety is less than 1. Here, the factor of safety is 1. And here, the factor of safety is more than 1. Clear? Now, we will consider the next plane. In the next case, when the soil is in a submerged condition, when the soil in a submerged condition, in that case, some changes are made into the soil. Again, we will consider the same, that is the cohesionless soil. Cohesionless soil. And here, this is the cohesionless soil. Again, we will consider the slope which is angle, making an angle beta. We will consider a slope of A, B, C, D of depth Z and the breadth of it is B. Now in this case, soil is considered to be the submerged. In the previous one, the soil was considered as a dry to hygienic soil, but here the soil is considered as a submerged soil. If the soil is in a submerged condition, in that case, there will be always the seepage will be act, and seepage is acting parallel to the slope. Seepage is acting in the direction parallel to the slope. So here, we will just consider this is W. This is the weight component of the soil which is acting vertically downward, and the another force that is considered as seepage force. Here we will consider this is the seepage force which is acting in the direction of the slope. And the soil is in a submerged condition. Because the soil is in a submerged condition, the density is considered to be the submerged density. Okay. So here we will just consider the soil or the water table is at the top. Here we will just consider the effect of seepage. As we will just consider here, there is an effect of the seepage. Now, what is seepage? Seepage force is denoted by PS, and where the seepage force will be acting, it will be acting in the direction of the flow. Where the water will flow, seepage force is also acting in the same direction. And then suppose this is the submerged soil, water flow is in the vertically downward side. If the flow is in this direction, the seepage is also in the same direction, and that seepage pressure or seepage force is denoted by PS. Right? So in this case, seepage force we will denote by PS. Seepage force is denoted by PS, which is equal to gamma submerged, which is equal to gamma I, that is the hydraulic gradient, multiplied by gamma W, multiplied by Z, multiplied by B. I is the angle of or the slope, which is denoted by sin theta. Then gamma W is the density of the water, and B is the width, and the Z is the depth. So here I is sin of theta. I is sin of theta. Then here this normal component, again we will consider the normal component and also the tangential component. So seepage force is parallel to the slope. Since the seepage force is parallel to the slope, therefore again we will consider the normal component. Here we will just consider this is the normal component N, and the another component is a tangential component, that is tau or the P. Tangential component causes sliding, normal force resisting the slide. This the N is the resisting force and P is the sliding force. Now what is T and what is H? Again we will consider the same condition as we have discussed in the previous case, and here we will now consider N dash is equal to W dash into cos theta. W dash into cos of beta. W dash into cos of beta, which is, what is W? W is, what is W? W is B into Z into gamma submerged, because the sulfate of the gauge. So it will be B into Z into gamma submerged into cos of beta. B into Z into gamma submerged into cos of beta. Then, as the soil is in submerged condition, gamma is replaced by gamma dash. As the soil is in submerged condition, therefore gamma is replaced by gamma submerged. Otherwise, it will be B into Z into gamma dash into cos of beta. Then what is T? Then what is T? T is W sin beta. Then T is W sin of beta plus Ps. Now in this case, there will be two sliding forces. In this case now, there are two sliding forces. One is the sliding of the soil wedge, which is denoted by T, and the another is the seepage force, which is also acting in the direction of sliding. So here, this T is, or the sliding force is equal to T plus Ps. Sliding force is equal to T plus Ps. Now what is T? It will be, what is T? It will be W into sin of beta plus Ps. So what is W? W is again B into Z into gamma dash. B into Z into gamma dash into sin of beta plus what is Ps? It will be sin beta into gamma W sin beta into gamma W into Z into B. Sin beta into gamma W into B into Z. Right? So here we will just have this things common, that is gamma dash plus gamma W. Gamma dash plus gamma W will take constant, and then B into Z into sin beta. Then another is B into Z into sin of beta. B into Z into sin of beta. Now what is gamma dash into gamma W? What is gamma dash plus gamma W? Plus gamma dash plus gamma W is gamma saturated. What is, how we will get this? Gamma dash is equal to gamma saturated minus gamma W. Gamma saturated, gamma submerged is equal to gamma saturated minus gamma W. Therefore, when we will consider gamma submerged plus gamma W, it will be gamma saturated. It will be gamma saturated. That is the saturated density of the soil. And therefore, this gamma saturated, it will be gamma saturated into B into Z into sin of beta. Gamma saturated into B into Z into sin of beta. Now again, we will come to the next part, that is the factor of safety. So again, what is factor of safety? Factor of safety is again resisting upon sliding. Resisting upon sliding. So what are now the resisting forces? Resisting forces are sigma delta, and what is T plus Ps? It will be T plus Ps, or it will be T plus Ps we have considered as gamma saturated into Pz into sin of beta, so it is considered as Q. Now here, what is sigma times Y? Sigma is gamma into B into Z cos beta into tan phi. So it is, what is the value of sigma then? What is sigma? Sigma we have already discussed, that is gamma submerged into B into Z into cos beta. Gamma submerged into B into Z into cos of beta. Gamma submerged into B into Z into cos beta into tan of phi. Then what is sliding force? Sliding force is gamma saturated into B into Z into sin beta. Right? So here it will be gamma saturated into B into Z into sin of beta. So again, this b will be cancelled, z will be cancelled, sin beta divided by cos beta is tan phi or tan beta, and therefore here this equation becomes here it will becomes gamma submerged upon gamma saturated into the remaining things will be cancelled, and here this is tan phi upon tan beta, tan phi upon tan of beta. So as again as in limiting equity, factor of safety is 1. As factor of safety is 1, therefore here we will just consider tan beta is equal to gamma submerged upon gamma saturated into tan of phi. Tan of phi, and in general, gamma submerged is half of the gamma saturated. In general, gamma submerged is half of gamma saturated. In general, gamma submerged is equal to half of gamma saturated, and therefore tan beta is equal to half of tan phi. And therefore, when the seepage is parallel to the the slope angle for in coarse grained soil is half of the friction line. Always remember that this condition is the worst condition, where the soil is in a submerged condition. The tan beta is half of the tan phi. This tan phi value is getting reduced to 50%. So this is the condition when the soil is in a completely submerged condition. The strength losses to 50%. Right? So this is the case for the cohesion based soil. Now the next part, in that we will discuss the cohesion in the stability of slope in the cohesive soils. Now when the soil is a cohesive soil in the infinite slope. So here next is cohesive soil. In the previous one, the soil was a complete cohesion based soil where the C value was C. Here the soil is now in a completely cohesion condition where the phi value is 0. And where some situations are occurs when particularly in clay where phi value is taken as 0. Phi is 0. Then what is the shear strength parameter? Here shear strength parameter is shear strength parameter is C only. The strength is due to cohesion only. Now again we will consider the same case of the slope. This slope is making an angle beta with the vertical. And in this case, this is A, B, C and D. This is A, B, C. In this case, here this weight component is W. W is the weight component which is acting in the vertically downward direction, and this B and this is Z. This is Z is the. So in this case again we will consider the same thing. Over here there is a normal force sigma or N, normal force N, which making an angle beta, which making an angle phi, sorry beta, and in this case it will be tau. That is the tangential force which is acting in the direction parallel to the slope, and that is the sliding force, right? So again, the normal stress on the failure plane. Suppose I will consider the normal here normal stress on the failure plane. Normal stress on the failure plane. And that is denoted as sigma. And here we will just consider this is sigma n, which is equal to n upon the area. That is n upon area. And here we will consider the area where in one direction is taken as unity. And therefore it will be b into 1, that is n upon b into 1. Now here, then sigma n is equal to what is n? N we already knows, that is n is what is n? N is cos beta. N is cos beta, that is w cos beta. Then here it will be w into cos square beta. W into cos square beta. Now what is shear stress? On the failure plane, and it's sigma also. Tau, it is tau n. Tau, which is equal to P upon B into L on 1 B into 1, and therefore this tau P is equal to gamma into Z sin beta into cos beta. Gamma into Z, which is sin beta into cos of beta. Sin beta into cos of beta. Sin beta into cos of beta. In this case, for pure cohesive solid, here it will be sigma n, and this that is tau b, normal stress or normal stress and the normal shear stress. So here, what is the equation of the shear strength for pure cohesive soil? So it is tau is equal to C plus sigma tan phi. As this sigma is, as this phi is 0, in this case, if phi is 0, therefore this tau is equal to C only. Shear strength is due to cohesion only. Shear strength is due to cohesion only, and therefore this factor of safety is equal to, what is shear strength? Shear strength is tau and shear stress is tau b, or we will consider it as tau f. Here this is, here we will consider this is tau f, shear strength, and this is tau p, that is the sliding stress. This is strength parameter, this is stress parameter. Strength parameter, stress parameter. So what is factor of safety? Strength divided by stress. So what is strength? Strength is tau f, it is tau b. So here it is tau f upon tau b. That is the shear strength upon shear stress. So what is strength? In this case, the strength is due to C, and what is this tau b? It will be gamma into Z into sine of beta into cos of beta. C upon gamma into Z sine of beta upon cos of beta, and therefore this is the equation of factor of safety. This is the equation of factor of safety for the critical condition. Now again we will come to the part that is where there is a critical condition. In the critical condition, the factor of safety is 1. Therefore, for critical condition, where factor of safety is equal to 1. In the critical condition, where the factor of safety is 1, in that case, Z is becomes ZC. In that case, Z is becomes Z. Here, Z is ZC. Z is becomes ZC, that is the critical. And therefore, this ZC is equal to ZC is equal to, from here I will just consider this ZC and factor of safety is 1. Factor of safety is 1. In that case, Z is becomes ZC. So ZC is equal to C upon gamma into sin beta into cos beta. Gamma into sin beta into cos beta. C upon gamma into sin beta upon cos beta. Now here, as Z is becomes ZC, that is the critical condition of the failure, where there is another dimensionless parameter which we have taken into consideration, that is called as stability number. So in the critical condition, for the given slope, this ZC is directly proportional to the cohesion. Z is in critical condition. In critical condition, Z is ZC, here factor of safety is equal to 1. Here the factor of safety is equal to 1. In this case, ZC is directly proportional to cohesion. ZC is directly proportional to cohesion and inversely proportional to the unity. Inversely proportional to the unity. If ZC is more, if cohesion is more, ZC is more. But if density increases, ZC becomes reduced. Therefore, ZC is directly proportional to C and inversely proportional to the density of the soil. If density is more, ZC will be less. And for a given slope of ZC, the dimensionless quantity called as stability number is denoted by S. And for this condition, the stability number which is denoted by SL is common picture purely in cohesive soil, and if there is a relation of ZC and C. So here this dimensionless parameter SL is denoted by C upon gamma into ZC. SL upon C upon gamma into ZC. So this is the dimensionless parameter which is called as stability number, and stability number, it can be identified, this SL can be determined from the graph that is called as Taylor stability graph, where the value of I or value of beta, that is the angle of inclination, then there is an angle of phi. This I and thus beta and phi are the functions. Sn is the function of beta and phi, which is particularly obtained. This Sn is obtained from the Taylor stability chart or the Taylor stability table, where the different values of Sn are given for beta and phi. Beta is angle of inclination. Sometimes instead of beta, it may be denoted as I. That I is the angle of inclination of the soil. So this Sn is obtained by Taylor stability chart. Taylor's stability chart, or obtained by Taylor. for different values of I and phi. So once you get the value of I and phi, you just refer the table, you will get the value of Sn. Many times in the equation, the I and phi will be given and C and gamma is also given. In that case, you have to find out the ZC. Sometimes the factor of safety is given and you have to find out the value of C. Sometimes you have to find out the capital H for a particular height where the slope is in a stable condition. So here, this stability number is obtained from the table. And when we are considering the stability number, we have to use the different equations. In this case, you can get the value of factor of safety from the equation. So this is the first one equation. Then the another equation, for determining the depth of temporary cut. Depth of cut. You will obtain the equation, that is factor of safety, or Sn is equal to C upon factor of safety into gamma into H. Gamma into H. What is H? H is the depth or the height of the slope. H is the height of the slope. ZC is the critical depth. Sometimes ZC can be replaced by H where the factor of safety is more than 1. Right? And if condition is critical, if in critical condition, if the condition is a critical condition, factor of safety is 1. Factor of safety is 1, and in that case, Sn is equal to C upon gamma into H. C upon gamma into H. So what is H now? H is the height of the slope. So Sn we have to calculate or we have to obtain from the table. Is it? So this is the case when the soil is a cohesive soil. Now the third part, when the soil is a C-phi soil. Mainly in the nature, the soil existing in the nature are the mixture of sand and clay. In that case, it will be considered as C-phi soil, where the equation of shear strength is tau is equal to C plus sigma tan phi, where the cohesion as well the friction is in the soil due to cohesion and friction in the soil. And that is called as C-phi soils. That is called as C-phi soils. C-phi soil. C-phi soil. When these soils are called as C-phi soil, when it possesses both sand and clay. It is having both sand and clay in the soil, then it will be called as C-phi soil. And what is the equation of shear strength then? Tau is equal to C plus sigma tan phi. Sand is having phi and clay is having cohesion. So this is the equation of the shear strength. So again we will consider the infinite slope, which is having angle A, B, C, E, W. This is W. In this place, here we will just take this B and this is Z. This is B and this is Z. Right? Now, what is the shear strength envelope? In the previous one, we have discussed the shear strength envelope. When we will plot the graph between the normal stress, sigma, and shear stress, tau, then there is a envelope is like this. shear strength envelope is like this, which is having making alignment phi with the vertical with the horizontal, and this is C, that is the cohesion component, that is the phi intercept. Now this is the case where the equation is C plus sigma tan phi. Here we can have this angle is beta angle. If beta is more than phi, in that case it may intersect at a particular point, and this is the failure point, or this is the point at which the critical condition, this factor of safety, is 1. If suppose this beta is less than this is the stable condition, right? Because it is running parallelly or it never intersects each other. In that case, it will be in a stable condition. Consider an infinite slope in C phi soil as shown in the figure, which making a slope angle beta, right? And in this case, we will just have an equation as we have discussed in all the previous cases. What is the factor of safety? Factor of safety is resisting upon sliding force. So here, what is resisting force? Resisting force is denoted as L, and here it is denoted as T. So L is which component of it will be a N cos beta. What is N? N is the normal component of the W. So here it will be N cos beta. So it is the normal component, and therefore N is W cos beta. N is W cos of beta, and here T is W of sin of beta. W cos beta upon W plus sin beta. So here this N is, what is W cos beta? W is, again we will put the value of W, that is gamma into Z into density and cos beta. So it will be, what is the equation over here? It will be C plus sigma tan phi, and here it is W sin of beta. So just put all the values as usual. Sigma, just put the value of sigma is W cos beta, and W is again, what is W? Here this is gamma into Z into B into cos of beta. So this is the value of sigma. The sigma value we will put over here. Sigma value we will put over here, and from this we will get the equation. We will get the equation for purely cohesive soil, and we have already find out it for the purely cohesive soil and for the pure sandy soil. Now we'll have an equation for factor of safety in C phi soil. Factor of safety in C phi soil, that will be C plus, it will be factor of safety C plus gamma into Z, gamma into Z cos square beta into tan phi into tan phi upon gamma into Z sin of beta into cos of beta. Now what is this gamma into Z cos beta? It is sigma. This is sigma. Sigma tan phi, C plus sigma tan phi into gamma into Z sin beta into cos beta. So this is the equation of factor of safety if the soil is a purely the soil is a C phi soil. Then it is subjected to seepage. Then we have already discussed it for the sandy soil when it is subjected to seepage. Then it is subjected to seepage. when it is subjected to seepage, then the same equation becomes factor of safety. Here it can be converted into gamma. It is C dash plus, instead of gamma, it will be gamma submerged now because the water table is lying somewhere here. So soil has become submerged. And what is gamma submerged? It will be gamma saturated minus gamma double. So here C dash plus gamma submerged into H cos square beta into tan of phi divided by gamma saturated. Here the most dangerous one is the self-rate of the soil, and which is directly proportional to the state of the soil in this zone. Gamma saturated is having the maximum density or the maximum self-weight when the soil is in a saturated condition as compared to the submerged condition. In this case, this is the worst condition where the resisting force is less and the sliding force is more when this gamma becomes gamma saturated. And here this gamma becomes gamma submerged. This here, this is the resisting force is less, and this is the worst condition in which it is gamma saturated H into sine of beta into cos of beta. So here this is the case. Just remember, the most important parameter is the density parameter. You just observe the density parameter. Here this density is same. This density is same when it is in a dry condition, but when it is in a submerged condition is assumed to be the worst condition. In that case, the resisting force is reduced as gamma is replaced by gamma submerged. Gamma submerged is having the least value out of all the values of density. And in the sliding force, it increases because gamma is replaced by gamma saturated. And therefore, this is the worst condition. Worst condition. Right? So in the next class, we will discuss the numerical based on all these things. So next class, we will having the numerical based on all the things, as well we will discuss the different Swedish circle method. Then there is a failure of the soil mass. All that things we will discuss in the next class.